Hello, I am Mike Wilbur, and I will be presenting our work on time-dependent decentralized routing using federated learning. As an overview for this presentation, I will start with the system model, motivation, and contributions. Then we'll move on to the background and challenges, which will lead into our approach to decentralized routing, as well as our simulated experiments and results, and we will conclude with the conclusion and future work. Our system is composed of three central components. Clients can be vehicles, smartphone applications, or GPS services. The second layer of our system is roadside units or RSUs, which are small server nodes that together make a decentralized network of fog nodes. On top of the RSU layer, there is a central cloud available for resource management and processing. Our focus is on vehicle routing services. Typically, these applications are hosted in a central cloud. However, what happens if the cloud is unavailable? Therefore, in this work, we make two major assumptions. The first assumption is that access to the cloud is intermittent or unreliable. A good example of this is during disaster scenarios when service may be interrupted. The second assumption is that there is a fog network of RSUs, which are city-owned and connected by a reliable subnetwork, which can remain active in disaster scenarios. Therefore, we would ultimately want to move the routing to the RSU level so that the routing services can remain active even when access to the central cloud is unavailable. Let's briefly discuss what this RSU network looks like. The RSUs are spread geographically throughout the transportation network as shown. We assume there is a reliable connection between RSUs, which might be a fiber optic cable or something similar. A couple of the reasons cities are looking into deploying RSU networks is for live camera feeds and smart stoplight sensing. With this architecture in place, we have spare resources available to host our decentralized routing application. The first motivation for this work is that by deploying routing applications at the RSU level, it can potentially remain operational during disaster scenarios. The second motivation is that this model moves computation closer to the clients, which can potentially reduce latency. This is particularly critical for future real-time technologies such as autonomous vehicle routing and path planning. The contributions of this work are as follows. First, we present a decentralized route planning approach and deployment model for fog networks. Second, we use predictive models to condense the search space and limit communication between nodes. This is critically important at inference time to limit latency. Third, to limit bandwidth requirements during training, we use federated learning such that the training occurs on the RSU nodes and only model weights are shared with the central cloud server. Routing services are critical components of everyday life. Google Maps processes millions of routes a day. Through their applications, users query remote data centers through smartphone applications. It's very important for industries such as shipping and delivery, as well as first responders. Let's look at the fundamental components of a routing service. Each query consists of an origin-destination pair, which is represented by a latitude, longitude geolocation of the vehicle's starting location and the destination location. Real-time systems require incorporating current traffic conditions to find the optimal route. Additionally, the network is constantly changing due to road closures or construction, new roads. Also, the routing service must be adaptive, meaning that it must handle wrong turns or changing conditions. To encode this information in the application, we can model the transportation network as a graph. Here we show what this might look like. In the diagram here, we can see that vertices are typically going to be intersections or points of interest in the network. The edges, therefore, make up the road segments. By modeling it in this way, it allows us to use shortest path algorithms such as Dijkstra or A-star for the routing services in our application. Now for real-time routing, we can model the edge weight as the time expected to traverse that edge. Now this requires integrating traffic conditions. We can get traffic conditions from smartphone data or perhaps speed sensors scattered throughout the network. Some of the examples of publicly available traffic data include the HERE API or INRIX. For our simulation and this work, we use the HERE API. The key takeaway here is that we need to model the edge weights as the expected time to traverse each edge. Centralized approaches involve hosting the routing application in a central cloud. To speed up computation, classic routing algorithms have been adapted to process the queries on multiple servers. However, these approaches assume constant time access between processes. This is a logical assumption for cloud architectures where communication between processes results in negligible latency. However, in a decentralized fog network, communication between RSUs can be a significant source of latency as messages are passed between each RSU to build the network graph for the route. In a decentralized model, each RSU has access to real-time conditions for a subset of the transportation network. Therefore, RSUs must coordinate network state to find the shortest path. As shown in the figure, we can assume a vehicle's query goes to the nearest RSU. If the destination lies outside of that RSU subgraph, the RSU must query neighboring RSUs to iteratively build a final route to return to the client. Let's look at an example. As shown in the figure, the shortest route lies along the communication path outlined in red. However, there are many ways to get to the destination. The blue path shows a communication path that returns a suboptimal route to the client, i.e. it returns a viable path that is not the shortest path. Classic shortest path algorithms that rely on depth-first search require significant communication overhead as the algorithm queries neighboring RSUs until the shortest path is determined. In a decentralized RSU network, messages would flood the system for each query, resulting in significant latency. Therefore, we need a new approach for adapting classic shortest path algorithms to run on a decentralized RSU network. To deploy the system, we first divide the transportation network into grids. Each grid is a geographical area that contains a local subgraph of the global transportation graph G. Each grid is then mapped to an RSU. Vehicles currently on this grid will communicate with the RSU in which it is mapped to. A cloud is also available to manage system metadata. This includes the mapping from the grids to the RSUs, as well as processing, which is available for model training, as we'll see in future slides here. Access to the cloud is assumed to be intermittent, therefore the routing application itself will be deployed only on the RSUs. Here is an example of what the grid RSU relationship looks like. We represent grids as a square region that contains a subgraph of the global transportation network. Each grid is mapped to a single RSU. Therefore, each RSU contains a collection of grids. This can be thought of as the RSU's local view of the transportation network. For queries that go to grids outside of the RSU's local view, communication between the RSUs is required. Let's look at an example of a query. First, the client queries the nearest RSU for the current shortest path to a location in downtown Nashville. RSU1 realizes that the destination is outside of its local view. Therefore, it sends a query to a neighboring RSU, RSU2, requesting the shortest path from the boundary between the RSUs to the destination. The destination is not in this RSU's local view either. Therefore, it returns to the requesting node that it only has a partial path and subsequently queries RSU3. When RSU1 gets the partial path, it updates the network state and waits for a path with the destination in it. RSU3 has a destination in it. Therefore, it returns a final path message to RSU1. RSU1 then performs a shortest path search on the return graph, which can be returned to the client. The fundamental question at this point is, how did we determine the correct sequence of RSUs to build the shortest path? We know that there are more than 3 RSUs in the network. How did RSU1 know to query RSU2, and how did RSU2 know to query RSU3? To tackle this problem, we use a predictive model called the grid routing predictor to predict the next RSU. In this way, the predictive model effectively condenses the search space and thus reduces the number of messages required to service a request. The grid routing predictor takes the current location, the destination, as well as the week of year, day of week, and the time of day. The grid routing predictor is a multi-class classification model that outputs the next grid to query. The use of predictive models can introduce significant bandwidth on the network. As shown in the diagram, centralized learning in the cloud requires vehicle and network data to be relayed to the central cloud. The model is updated in the cloud and then pushed back to the RSUs to be used for the routing application. To solve this problem, we use recent advances in federated learning to move training to the RSU layer. As new data is relayed to the RSUs, each RSU performs local updates. Periodically, the RSUs transfer the updated model weights to the cloud, where the results are aggregated through a global update step, and the new global model is pushed to the RSUs. In this way, our approach avoids costly data transfer between RSUs and the cloud. Additionally, this architecture avoids transferring raw data to third-party cloud providers, since all traffic information is processed on the city-owned RSU network. To investigate our approach, we set up an experiment where we divided Nashville into over 1,000 grids serviced by 5 RSUs. For the global base map, we used OpenStreetMaps. The traffic data was collected from the Here API, where we used 4 weeks for training and 1 week for testing. We synthetically generated 1 million source destination pairs to simulate routing requests on the network. We compared our approach to multiple current state-of-the-art routing algorithms. We found that our approach is faster than comparable parallel approaches. Additionally, our simulation did not account for increased latency for services running in the cloud, which would have negatively impacted the results of the 4 other methods we compared to. We also measured CPU and memory consumption during the simulations. For non-parallel methods, we divided the resource demand by the number of RSUs to compare directly with our approach. We found that our approach had efficient memory usage. Our approach had fairly high CPU utilization, mainly due to the repetitive routing between boundary nodes between the RSUs. Due to our reliance on data-driven prediction to identify the next RSU to query, our approach was not guaranteed to return the optimal shortest path. Therefore, we also documented the accuracy of the routes returned for each simulated query in the simulation. We found that our approach returned the optimal shortest path 91.6% of the time, a non-shortest path 7.6% of the time, and no route was returned for 0.8% of the requests. It is important to note that our method is data-driven. Therefore, the performance of our approach is only as good as the trained models. As our models are trained online, the system is expected to improve over time in operation. For our model, we used a deep feed-forward neural network. We found that model convergence only took moderately longer using federated learning compared to traditional learning. In this work, we presented a decentralized route plan approach and deployment model for RSU fog networks. By using predictive models, we were able to reduce communication overhead at inference time between RSUs. To limit bandwidth requirements, we used federated learning for model training. Through a simulated experiment, we found that our approach is faster than comparable parallel approaches. We are currently looking at implementing our approach in a middleware designed for smart city RSU fog networks. Additionally, we are focused on extending this work to handle node failures.